warm weather, you seem to feel hotter if you're wearing black than if you're wearing white. Is this just your imagination, or are black things really warmer than white things? What could color have to do with heat? What is color anyway? Why are tomatoes red? Or oranges orange? Or buttercups yellow? Or green peas green? Or blueberries blue? Or violets violet? Where do all these colors come from? They come from light itself. White light contains all the colors. See for yourself. Go into a dark room. Open a chink in the blinds and let a narrow beam of light in. Now hold a glass prism in the light beam. Look at the colors. Red, orange, yellow, green, blue, violet. That's what white light's made of. When it shines all these colors on a tomato, the tomato absorbs each of the colors, except red, which it reflects. That's why tomatoes look red. Oranges do the same. They absorb all the colors, except orange, which they reflect. So oranges look orange. Buttercups only reflect yellow, so they look yellow. The same thing applies to green peas, blueberries, and violets. Now, if you mix all these colors together again, you get white light once more, because white is simply a combination of all the colors. Your white suit appears white because it doesn't absorb any of the colors. It reflects them all. On the other hand, your black suit appears black because it absorbs all the colors. It doesn't reflect any of them. Black is simply the absence of any color. But what's all this got to do with black being warm and white being cool? Well, when the sun radiates waves of heat energy, these waves come in many different forms, which make up a whole band, or spectrum of energy waves, from radio waves at one end to X-rays and gamma rays at the other. Some of this heat energy is visible. These are the light waves made up of all the different colors, but these only take up a little bit of the radiation spectrum. The rest of the spectrum isn't visible at all. There is, for example, some invisible radiation just beyond or beneath the red. Since the Latin word for beneath is infra, this is called infrared radiation. Now, most of the sun's radiant heat energy comes to us in the visible and the infrared parts of the spectrum. And that's why black is warm, because it not only absorbs the heat energy of the visible colors, but in doing so, it also tends to absorb a lot of the heat energy of the invisible infrared radiation as well. Conversely, white is cool, because it not only reflects the heat energy of the visible colors, but in doing so, it also tends to reflect a lot of the heat energy of the invisible infrared radiation. So now you know that color really does have something to do with heat. It isn't just your imagination. You also know what lies at the end of the rainbow. It isn't a pot of gold. It's infrared radiation.
All right, a little summary about that. Black box. You have two black boxes in your body. Your eyes are a black box. It's called a black box because basically light does not escape from it. Notice the box is painted white inside. But when she closes the top, notice here, when there's light, we see white. Now, is there light going in through the hole? Yeah, there's light going through the hole. I mean, if you were standing inside the box, would you see light from the outside? But because basically the light bounces around the inside, it doesn't get back out. This is what happens to your eyes. Because your eyes, what is the color inside of your eye?
I can't see it.
You do see it when you take. Sometimes when you take pictures, you see it. It's red because of all the blood vessels inside in your retina. The interior layer of your eye is red. If they've ever taken a picture of your retina, sometimes your ophthalmologist might take a picture of your retina, it would be red.
Through all the black stuff.
There's nothing black in there. Your eye is hollow.
What? I dissected a cow eye and it's like black.
That's a cow eye.
Oh, they're different?
They're different. Shh. But remember, your eye is hollow. It's filled with a clear fluid.
Oh yeah, that's right.
Vitreous fluid. If you've ever dissected an eye, it kind of jellifies. It's better if you do fresh eyes. You know, maybe I'll try to do that when we do light. Maybe I'll try to get some fresh cow eyes. Literally, the first thing I did when I went the last physics institute I went to, the last physics basically summer institute I went to, the very first thing we did was dissect cow eyes for light, because a fresh cow eye, fresh eyes, the lenses are clear. In other words, if you go down to the slaughterhouse and you get the eyes that have just been, they're fresh and not preserved, the lenses are still clear. Yes. Well, that's where I did it. All right. So this is also why when you take that flash that turns red. Now, if you ever see a cat's eyes, you catch a cat at night, they glow green. Because cats, like a lot of animals like cows, they have actually a reflective surface on their retina that allow them to collect more light so they can see in more low light conditions. Our eyes actually need a lot of light to work properly, but this is the black light. Now, no. Our eyes are pretty much optimized for what they do. But cat's eyes can't do a lot of things we do either. So, all right, Newton's law of cooling. Shh. Newton's law of cooling. Same guy, Isaac Newton, the guy we talked about in mechanics. And this also works for warming. By the way, what we talk about for cooling is same for warming. It could be called Newton's law of warming. And it's the greater the temperature difference, the greater the rate of warming and cooling. So our rate of cooling, and remember that could also be warming, is directly proportional to the difference in temperature, our delta T, the difference in temperature. So the greater the difference in temperature, and you see that.
What's the squiggly line mean? Does that mean it's
That proportional to. So it's proportional to that. There we go. So the greater the difference, actually you see that in that conduction equation. In your lab, you had that theoretical conduction, TH minus TL. The greater the difference between TH TL, the greater your rate of conduction is going to be. By the way, in your lab, just to let you know, your theoretical rate of conduction should have come out around 10 joules per second. So, for actual or theoretical? That sounds good for actual. Theoretical should be around 10. Actual is going to depend on what you actually measured. But the theoretical should have come out somewhere around 10. You know, because the temperatures we're using, that's about where it should have come out to be around, somewhere around 10 plus or minus 1. All right. Now, there's a classic problem. Everybody got this down? I mean, not got it down. The classic problem is what to do to your coffee. Do you leave it black do you let it wait and then add your cream before you drink it? Or do you add it immediately, for those of you who like to wreck your coffee? We do not even have enough time to go into that. Anyway, this is a personal thing. So our coffee starts at around 60 degrees Celsius or so, 60, 70 degrees. You might notice that was the very starting temperature. We got out of the coffee urn. It comes out a little bit somewhere between 60 and 70 degrees Celsius. Now, The question is, if I want the hottest cup of coffee when I go to drink it, I'm going to let it sit for a while to cool off, but I want the hottest cup of coffee possible later. Do I add my cream immediately, or do I let it cool and then add my cream just before I drink it?
Add it immediately. Cool.
Well, let's talk about this. Well, first of all, the first cup, I'm going to cream it. Shh. I'm going to cream it. And basically, by creaming it, I immediately reduce its temperature to 50 degrees Celsius. I go down by 10 degrees. And so I wait about 10 minutes. And after about 10 minutes, my temperature is now about 38 degrees Celsius, which is about a little above body temperature. This one, I wait that 10 minutes, and at the end of 10 minutes, it's at 45 degrees. Now, it's still hotter than my other one. You might say, well, look, it's hotter, but now I have to add the cream. So now we cream it. And creaming it basically reduces our temperature by how much? 10 degrees. So now we're at 35. And so it ends up being colder. And the longer you wait, the colder it's going to be at the end. Even though, like me, if I was going to drink my coffee black and let it sit, it'd still be hotter. But the reason is, by immediately putting in the cream, I reduced my temperature. So in other words, what did I do to the rate of cooling? I reduced it. I reduced the rate of cooling. So this one cooled at a much greater rate than when I added that little blivet of very cold liquid. It had a much greater effect. Where here, did you get your hand caught in between something?
I hit my hand on the desk.
Okay. So this is the thing. So those of you who like to do this to your cream, shh, you know what to do, or your coffee. All right. One last thing. Greenhouse effect. First, let's talk how a greenhouse works. A greenhouse. Now, we live in California. You don't see too many greenhouses in people's backyards. Unless they're like orchid growers or something. But still, we don't see... You see them commercially, like out at Half Moon Bay. They have the commercial ones and things like that. Yeah. Commercial ones, right? Big ones? East Palo